And at some point we started making galaxies and stars, and then we are here. And of course this is because it was done by WMAP. Of course the whole universe has evolved to produce the WMAP satellite. No. It's an inside astronomer joke. Okay, so I talk about the size of the universe. Again, I had to cover 2,500 years in less than 1 hour, so I took many shortcuts. As always, many people had the wrong ideas, many people did it wrong, and so, you know, we don't talk about them, we always talk about the successful ones. Where does the Earth fit in here? Well, we actually have a very good measurement of the age of the solar system, very precise measurement, namely we can do radioactive dating of rocks on Earth. The oldest rocks on Earth are about 3.8 billion years. We brought the samples from the moon. They're somewhat older because the moon is basically had very little volcanic activity. It's by now not active. So the rocks, anytime a rock melts, it releases the gases that are produced in reactive decay, and basically the clock starts new. So if there is volcanic activity, you only measure the age, you only measure the time to the last melting of the rock, if you will. If you have less volcanic activity on the moon, you see older rocks, but the oldest rocks actually we measure this way are the ones that come from space, namely they're called meteorites. Meteorites on Earth, lands on Earth, we can do radioactive dating. And this point, number of them gives us 4.54 billion years. And that's the age of the solar system. And that agrees with the age of the sun, which we get from this other method I described. So we are kind of late newcomer in the universe, roughly, you know, after 2/3, well, 14 billion, and the Earth has been around for 4 billion. It's actually probably not really coincidence. This is again a separate talk. It takes a while to build metals. The original universe starts with just hydrogen and helium. After the Big Bang, these are the only elements I have. All the other elements have to be made in stars. So in order to make iron, carbon, oxygen, and all of these ones we like and breathe and so on, they were made in stars. But you have to make stars first. And by now we understand very well that more metals, what we call metals in astronomy, you have, the higher a chance of having a planet. So the fact that we're sitting on a planet as an observer, that actually preferentially puts us later in the universe. It's not a proof of anything, but it's actually kind of, it makes sense that we don't live around the star, which is, let's say, 11 billion years old. The sun is relatively young, and it's relatively metal rich. Okay, so I talk about the past, I talk about the age. What will happen in the future? Again, that could be a whole different talk. Turns out the stars will evolve differently. Our own sun is again 4.5 billion years old. We'll live for another 5 or 6. We'll sit there, burns hydrogen to helium in the core. What you say, you know, many hydrogen bombs at a given second are exploding in the center of the sun, but they're contained by the sun. We convert energy by converting hydrogen into helium. At some point you exhaust the fuel, the star will evolve, will go through the stage of the red giant. At this point, the life on Earth will cease, at least the life as we know it, because the sun will swallow Venus, and the temperature on Earth will be, you know, a few thousand degrees. Now, if we don't figure by then how to, you know, leave, then it's kind of, we have 6 billion years, so I think we can kind of deal with the idea. At some point, this envelope of the red giant separates from the star. We see this as so-called planetary nebulae, and then you have one of these white dwarfs left around that I already mentioned we see in globular clusters. If sun was a much more massive star, it would go a different route. Actually, it would explode as what we call a supernova. And we also see these on the sky. But for that, you have to be about 8 solar masses. So in our own case, the sun will still do some exciting things, but actually will not really explode. It will not end the life in explosion. Here you have to be a pretty massive star. So we understand the future of the solar system pretty well, and the Earth, again, will get hotter and hotter and hotter, and nothing to do with the greenhouse gases. It's just the sun it's becoming more and more luminous. The sun really started about, I think it was 0.7 solar luminosities when it was first born. So the sun has been getting hotter all the time, just because it's slowly exhausting the fuel. What about the universe? I mentioned the Einstein equations, really, the GR equations for the universe allow you to do this. You always start expanding, and then if you're a low density universe, you keep expanding. The analogy is if I throw a ball, but from a small, you know, from an asteroid, the asteroid doesn't have much gravity, so the ball will just keep going. If I throw a ball up from Earth, Nobody has an arm like that. You have to throw the ball at 11.2 kilometers per second in order for the ball to escape. Even, you know, Louisville slugger, there's just not, no. I took a picture, it's quite impressive, the big baseball bat. If the universe is very dense, I throw the ball up, but the gravity at some point says stop, and the ball falls down. The same goes for the whole universe. Actually, the equations are mathematically the same. The universe is expanding, but because it was too dense, at some point the gravity stops the expansion, and the universe will collapse. These were the two possibilities by Einstein. Einstein put this lambda term basically to make the universe kind of sit there. It turns out that wasn't really, he was correct that it would do it, but it would only do it briefly. The universe actually would not have it. This is not a stable solution. The universe would still either continue to expand or contract, even if you kind of artificially stopped it. So this is what we all learn in grad school, namely the universe can keep expanding or can shrink. By early 90s when I was going to grad school, we were kind of closing on this solution. What we didn't expect is that not only the universe is actually expanding, but the expansion is actually accelerating. This is the third solution where I throw the ball up, and the ball never falls. In fact, it keeps going up faster and faster. And that means there is some additional force in the universe that this will do so. I mean, they only allow things in the universe are such that you actually have some physical force on it. It turns out if you look back at the Einstein equation, the lambda will actually do it for you. The lambda, it's described as energy of vacuum. As the universe grows, don't ask me, nobody knows. As the universe grows, there is more and more space. So the energy of vacuum takes over, and once the energy of vacuum takes over, the universe has a runaway expansion. It starts expanding exponentially. We're not there yet. We are kind of in the transition phase. But this was the big discovery of 1998. And these three gentlemen, actually relatively quickly, last year in 2011, they got the Nobel Prize, Physics Nobel Prize for it. So this whole permuter from California, and Brian Schmidt, he's now in Australia, but he was at the time in America, and Adam Rees, he's, I think, at Space Telescope now. There were the three people, but in fact, as often happens in astronomy these days, in each case, in Perlmutter case, there were about 40 people on the team, and in this case, there were another 20 people on the team who did the observations. And that's, again, a separate talk, but not only the universe is expanding, but our new knowledge, maybe last decade or so, that the expansion of the universe is accelerating. So in this scenario, a distance to any two objects in the universe is not just increasing, but it will continue increasing faster and faster. And at some point in the future, we won't be even able to see the galaxies because the light to them will never get to us. So this is my last slide. Thank you very much. And I believe there are always time for questions.
Hello, thank you very much to Dr. Stanek for an enlightening and horizon-broadening talk. So we open up the floor for questions now. Anybody got questions for Dr. Stanek?
Yes, sir. Just like, so it's very different from the solar system. In the solar system, everything moves around the sun because the sun has 99% of the mass of the solar system. In the Milky Way, there is a black hole in there, but it only is about, it's only about 1 million solar masses, 4 times 10 to the 6, and the whole Milky Way is many times more mass. But basically, the way we understand it, if there's any initial angular momentum, namely there's a sense of rotation in the cloud that then collapses into the Milky Way, then there is a center. So there is nothing special there in the beginning. Eventually things kind of, some galaxies have monster black holes in their centers, like 1 billion solar masses. We only have 4 million solar masses black hole. That's a lot, but compared to some other galaxies, that's actually a fairly small black hole. No, so this is something anytime I teach astronomy, and this is a very good question. Basically, if you actually think about the Hubble expansion and you now shift yourself to another galaxy and ask, what would this observer see? They would see exactly the same thing. Because they're moving away from us, but then if I shift to their point of view, I am moving away from them. and then the whole pattern repeats. So naively, you would imply that we're the special observer, and it's true, but this is like the Lake Wobegon. Everybody is special. Namely, everybody, I think that's, everybody is kind of in the center of the expanding universe. So from that point of view, the best analogy is, a good analogy is if I took, you know, started stretching, you know, people have the analogy of baking a pie, and then any two raisins in the pie are moving away from the other raisins. Of course, the pie has limited size and so on, and the universe doesn't. By the way, when I say we have size of the universe, we can only measure the size of the universe that we actually see. Is the universe actually, to the best of our knowledge, is infinite or at least very large? Namely, we don't have that measurement. There's a universe outside what we can see. We can only see things as far as the photons got to us from the beginning of the universe. And so, of course, the longer we wait, we'll be able to see a little bit more, but then the runaway expansion kicks in, and then we're actually able to see less and less of the universe. But that's again, many billions of years in the future.
What will the James Webb Telescope add to Hubble and, like,
Oh, very much so. So it is expensive. I think it's a few $1 billion again. Hubble turns out it's, by now, I think if you added all the money together, it's about $5 billion. But, you know, again, that's half of an aircraft carrier and no planes included. So, you know,